the objective, or you can say that the aim of this class is to understand how to calculate the change of entropy for some important processes. Okay, so we already know about entropy changes for some processes, and in this class we basically concentrate on 4 important processes, which are actually, number 1 is your expansion for ideal gas. Okay, and the second one is the phase transition. Okay, that means the entropy changes for the phase transition, maybe from solid to liquid or liquid to gases. Okay, so what is the change of entropy for this type of phase transition we're going to study. Okay, number 3 is, or number C is your heating. During the heating process, some entropy maybe not maybe it definitely the change of entropy will going to occur, because heating, in case of the heating, the randomness of the system will going to definitely increase, and we know that the entropy is actually directly related to the randomness. Okay, so that's why heating is also an important process. Okay, so we're going to discuss this one also. And the fourth one is your measurement of entropy for different process. Okay, so this 4 we will going to discuss one by one. Okay, but in this class we will going to discuss mainly this first and second one. Okay, and the third and fourth we are going to discuss in the next class. Okay, so our aim is to mainly discuss this one. Okay, so why this is important actually, why we actually want to study this topics. Okay, the change of entropy, why this is important, because we know that the change of entropy mainly related to what this will going to relate with to the spontaneity of a reaction. Okay, and by by knowing the value or the magnitude of this del S, that means entropy change for that process, we can have some idea about the spontaneity of that process. Okay, and actually it is not alone, it will not going to determine the spontaneity of the process. Actually the del G, which is actually Gibbs free energy, will going to mainly determine whether the process is spontaneous or not. Okay, so we're going to discuss one by one in details. Okay, so let us first discuss about the first one, which is the expansion of ideal gas. Okay, so for that, let's suppose we have, so first one is what? First one is your expansion of ideal gas. Okay, so for the expansion of ideal gas, we need some ideal gas first of all. Second, what we have to do, we have to expand the gas. So let's suppose we have a system, and the system is, let's suppose this is a cylinder. Okay, so we have a cylinder, let's suppose, with a frictionless piston. Let's suppose this is the frictionless piston. Okay, so this is the frictionless piston, and this is the cylinder. Okay, so suppose we put this ideal gas inside this cylinder. So let's suppose this is the piston initially at the position I. Okay, so here inside this cylinder ideal gas is present. Okay, so and suppose the volume of the ideal gas at this position, that means when the piston is at I, then the volume will be Vi, suppose. Okay, and suppose that the ideal gas can expand. Okay, so if it will going to expand, then what will going to happen? This piston will going to move this direction, this direction. The piston will going to move this direction, then only the volume of the, that means the expansion of the gas will occur. Okay, suppose this this gas will going to expand, and this expansion actually the system will going to do the work. Okay, actually we did not do any work, external work. Okay, the work is done by the system. Okay, so let's suppose the piston, after expansion of this gas will be at this position, let's suppose. Okay, so let's suppose this is a final position. So the volume, that means the volume from this one, that means the volume will be this one, no? After the expansion, this one up to this one. Okay, so let's suppose the volume for the final volume will be your Vf. Okay, Vf, let's suppose the final volume will be Vf, and the initial volume, that means at position this one, initial volume is equal to Vi. Okay, understand? Now since this process or this expansion process is what, this process is done by this system, then the total work will be, we can write the total work, integration of Vi to Vf dw. Okay, here we consider that the process is reversible. Okay, the process is reversible. So if the process is reversible, then only we can write dw. Okay, small d, we can do the integration. If the process is not reversible, that means reversible means what, the expansions occur infinitesimally. Okay, that means the volume will going to increase infinitesimally. Okay, understand? That's why we can write the dw. So this process is reversible process. Let's suppose this process is reversible process. Okay, so the work done by the system is also reversible work. So this W represent the reversible work. Okay, so W total, this is the total work done by the system. That means the ideal gas done by the ideal gas when the expansions occur is equal to W is equal to integration V initial to V final dW. Okay, so we know that W is equal to actually P dV. Okay, where dV represent what, the change in volume, that means this part from here to here, the change in volume is here, no? But here it is actually not dV, actually this is integration of dV, no? So integration Vi to Vf. But the thing is that this work is done by the system, so we have to add one negative symbol or sign here. Okay, again, in the initially we already considered that this gas is what, ideal gas. Okay, so if the gas is ideal gas, then what we can say, that we can say that since the gas is ideal, so this is what, ideal gas. So since the gas is ideal gas, so we know that ideal gas follows some equation, one equation, no? That equation is known as ideal gas equation, and that equation is equal to PV is equal to nRT, where P is the pressure of the gas, V is the volume of that gas, pressure means, I hope you understand this thing. Okay, and N represent what, the number of moles of that gas, R is the gas constant, and T is temperature. Okay, so here you see here this is the reversible work done, and here this because this is what, this is in case of ideal gas, so we can replace this pressure by this pressure, so we can write here P is equal to nRT by V. Okay, so you can just put the value here, understand? So now it will become like this, you see, W. So from this equation we can write W is equal to minus Vi by 2T Vf. In place of P we can write nRT V dV. Okay, so this part, if you see this part, then you see here capital that N, small n represent what, number of moles. So this is constant because at that cylinder, the number of particles or number of gas will be same, because we are not introducing any matter from outside, that means any gas from outside, so the number of moles will be constant. Okay, number of gas molecule will be constant, so we can write this one outside from that integration, we can write this one outside now. And again we know that R is also constant because this is a gas constant. Okay, the thing is that here T, capital T, we actually consider this process as isothermal process. Okay, we consider that the process is that means this process means what, the expansion process. Okay, the expansion process is actually isothermal process. So if the process is isothermal, then temperature is also constant, because we know that in case of isothermal process, dt is equal to 0, or what we can say, T is a constant. Okay, so we can write T outside from integration. Okay, so Vi to Vf, here what we can write, only dV by V. Okay, so we know that integration of 1 by x dx is equal to actually log ln x. Okay, ln x. So we can use this formula. So here we can use this formula, or if you can write a to b, then it will be what, actually ln b a. Okay, because ln b minus ln a actually, so we can write this one. So you can use this integration formula, and we can write here w. Okay, total work w is equal to minus nRT. Here we can write ln Vf divided by Vi. Okay, so here actually ln means log base e. Okay, I hope you know these things. Okay, actually ln is equal to log base e, same thing. Okay, or this is equal to 2.303 log base 10. If it is log ln x, then here you can add x. It's all mathematics. Okay, so here we have these relations. W, that means the total work, it's actually capital W. Okay, total work is equal to minus nRT, that is the work done by the ideal gas on expansion is this one. Okay, but our aim is to what? Our aim is to calculate the entropy change. Okay, our aim is actually to calculate the change of entropy. So here we know that the del S, that means the change of entropy, is defined as Q reversible, because this is for the reversible process. Okay, actually this definition is for reversible. Del S is equal to Q reversible divided by capital T. Okay, so we have this formula, or we have this, we know already this relation. Okay, so we know these things, but here how, because but here we don't have these values. Huh? We need this Q reversible value, but here you see we have the work. But can we get the Q reversible value from this work? Yes, definitely we can get, because because the thing is that we know that from the first law of thermodynamics, we know that del U is equal to Q plus W. Okay, so that means the change of internal energy is equal to actually the change of that heat for the reversible process is equal to plus W. Okay, so we can use this formula. Okay, this formula to actually, here you see again we know that for this process actually the change of internal energy equal to 0. Okay, there is no any change of internal energy. The internal energy will be same, because we did not actually, we don't apply or we don't introduce any external energy or any, because internal energy will be changed only when we add some matter or add some external energy in the form of any form of energy. Okay, maybe heat or any energy, then only the internal energy will be change. Okay, but here we don't apply any external energy or what, or matter. That means this will be equal to 0. So that means what we can write? We can write that Q reversible is equal to minus W. So we have this relation now. So we have now, you see, that means we can write here Q reversible is equal to nRT ln Vf by Vi. Understand? Clear? So now you see here, so we can put this value, Q reversible value, here. That means here, that means del S is equal to what? That means del S is equal to become nRT ln Vf by Vi divided by T. That means T cancel, nR ln Vf by Vi. Understand? So we can write on it. So that means the del S, the change of entropy, will equal to Q reversible divided by T. So in place of Q reversible, what we can write? We can write nRT ln Vf by Vi. Okay, so here divided by capital T, so it will be your nR ln Vf Vi. So this is the actually your change of entropy for expansion of an ideal gas. But this is for what? This is for the change of entropy for the system. Okay, change of entropy for the system, not surrounding. Okay, please remember this point. So del S represent actually what? The change in entropy during the expansion process, actual change in entropy because of the expansion for ideal gas. Okay, for ideal gas, but this is for what? Change of entropy actually of the system. Okay, of the system, this is very important, of the system during the expansion of ideal gas, not the surrounding. Okay, so again the thing is that here del S, so actually the S is what? S represent your entropy. Okay, so we know that we know one important point, that is the entropy is a state function. So what is the meaning of a state function? The meaning of a state function is that the entropy, the value of entropy or the magnitude of entropy will not going to depends upon the path whether it via which it will going to get that position. Okay, so if we calculate the entropy for a state, then you know the entropy of the state will not going to depend upon the path. That means let's suppose here at this state the entropy is S1. Okay, and let's suppose that at this state the entropy of the system is S2. Same system. Okay, but the state will be different. Let's suppose. Okay, so here suppose we are going through a reversible process, or let's suppose we are going to a irreversible process. Okay, so at this position it will be always S2. That means the entropy value is always S2 whether we are going to go this path or this path. Understand? So a state function. So that means this equation, that means del S is equal to, that means del S is equal to nR ln Vf by Vi. This equation. Okay, so this equation does not depends upon the path. Okay, that means this equation is applicable for reversible as well as irreversible process. Understand? So this is very important. Okay, so this relation, that means we can calculate the change in entropy, for the expansion of an ideal gas for reversible and irreversible process by using this same equation. Clear? Again, if you look at this equation, see here the equation is what? The relation is del S is equal to nR ln Vf by Vi. That means this the physical significance, if you we can actually express this one graphically now. So we have this relation del S is equal to nR ln Vf by Vi. So here actually this del S, that means change in entropy, is actually related logarithmically. This one actually exponentially it will going to increase. Okay, so here I am giving the graph. Here the x-axis represent del S. Actually here del S by nR is equal to ln Vf by Vi. Okay, so here we represent this one y-axis del S by nR, and x-axis Vf by Vi. Okay, so here it is actually increase exponentially. Okay, so because the logarithmic actually increase in the entropy of a ideal gas as it expand isothermally, because this is an isothermal process. Okay, so now we able to know that this change of entropy that means for this expansion process is independent of the path. Okay, that means whether it is reversible process or irreversible process, we can use the same equation to calculate the change in entropy. Okay, but the thing is that the total change of entropy actually relate the total, but the thing is that the total change of entropy is depends upon the path. Okay, so actually it is not like this one. Why? We can actually understand this point by using some example. Okay, so the main thing is that the total, so please remember this point, the total change in entropy is related to the path via which the expansion take place. Okay, so we can prove it by using an example. Okay, let's suppose we have some system. Suppose this is our system. Okay, so we are going to prove this point. Okay, why this is this total change of entropy is depends upon the path. Okay, so please remember this point. Okay, so we are going to actually prove this point by using an example. So let's suppose this is a system, and here let's suppose we are going to apply some we actually introduce some heat from the surrounding to the system. Okay, so if we introduce or if we add some heat and energy from the system to the system, then let's suppose the change of that system heat will be dq, let's suppose. Okay, then if we introduce from the surrounding dq amount of energy, okay, then there will be a decrease of heat. That means the same amount of energy will going to decrease in the surrounding, because that amount of energy will going to introduce to that system. Understand? Clear? Because that amount of energy we actually introduce. That's why this amount of energy will going to decrease in the surrounding. Okay. So what we can say, that the amount of dq, that means the surrounding, that means the amount of the heat which is lost by the surrounding is equal to actually gain by that system. It means minus dq. Understand? Again, that is if we add heat to the system from the surrounding, the increment of the heat in the system will equal to the heat decrease in the surroundings. The meaning of this is that, okay, this equation is that. So for reversible process, okay, reversible process. So for reversible process, what we can write? So for reversible process, we know that del S surrounding is equal to, we always know that mainly for reversible process, del S is always equal to Q reversible divided by T. Okay, but here it is surrounding, so we have to write here surrounding. Okay, but the thing is that here Q surrounding is equal to actually dq. So in place of Q surrounding, we can write Q reversible actually, because this is actually reversible process. Okay, understand? So it will be your T, but here you think, see, this is not negative, so we have to write here negative. Understand? Clear? The same thing here, we just dq surrounding is equal to dq, but here what we write, dq q surrounding is equal to minus q. If you want to write d, then you can also write here d. Okay, no problem. dq surrounding, dq reversible, same thing, no problem. Understand? Now we know that here we again know that q reversible is equal to from the previous notes, we already know that q reversible is equal to actually w. So here it will become what is equal to actually minus nr ln vf by vi. Okay, vf by vi. So it will del S surrounding. Okay, so that means you see here for the system del S, that means the change in heat, change of that entropy. Okay, change of that entropy is equal to nr ln vf by vi. That means there will be an increment of what, the entropy. Okay, there will be an increment of the entropy because this is a positive sign, but here the amount of increment is actually the amount of decrease. Do you understand this point? You see here this is the system. Okay, so when we add the amount of heat to that system, that randomness will going to increase. So how much randomness will going to increase? How much actually amount of the randomness will going to increase? The amount of randomness increase in this system is equal to the amount of randomness which is decreased in the surrounding. The meaning of these two is that this one and this one. Okay, this one is actually increment of the entropy in this system, and this is actually the decrease of the entropy in the surrounding, and these two are actually equal. You see, the magnitude is equal. That means the total entropy, if you want to calculate the total entropy for the reversible process, okay, so that means the total entropy change, okay, change of that reversible process of the reversible process, reversible expansion, but here it is isothermal. Okay, isothermal expansion is what? S del S total is equal to del S, which is represent the change of entropy for the system, and del S surrounding. Okay, so it will become what? 0, because this, if you put this the value of this one, then at this one, then it will be cancel each other. Okay, then it will become 0. So del S total for reversible expansion, that means isothermal expansion, will always equal to 0. Okay, so we have this value now. So that means for the reversible process, the total change of entropy is equal to 0. Now let us calculate for the irreversible process. Okay, so for irreversible process, actually we can we can calculate this one by using this concept. Okay, let's suppose, but if the process is isothermal, free expansion and irreversible process, then we know that W is equal to 0. So for, let's suppose, for now we are calculating for irreversible process. Okay, irreversible process. Okay, so for irreversible process, we know that if the process is irreversible, and also let's suppose this is a free expansion. Okay, it is free expansion, then W is equal to 0. Because why? Because P external is equal to 0, because we know that W is equal to actually P external into dV. So if it is 0, then it will be that W is equal to 0. Understand? So W is equal to 0. Again, we know that W is equal to actually what? Again, from that Q. Understand? W is equal to Q, because from that first law of thermodynamics, we know that del U is equal to Q plus W. Understand? Clear? But here actually minus. Okay, so here this is the from the first law. So Q, because this is equal to 0, internal change of internal energy equal to 0, because we are not adding any external heat, so it will be 0. So Q is equal to minus W, or W is equal to minus Q. Again, we know that W is equal to 0 for reversible process for free expansion, so Q is equal to your 0. Okay, so if the Q is equal to 0, okay, if the Q is equal to 0, the del S for the what? For the surrounding is equal to what? Q by T, so it is equal to also 0. Understand? So that means the total change of entropy for the irreversible process for free expansion is equal to what? Del S plus del S surrounding. But here this part is equal to 0. Okay, so we have only, that means what we can write, 1 minute. So what we can write that del S total is equal to NR ln Vf by Pi. Okay, so here in case of for irreversible process, we are able to know that the total change of entropy for the expansion process is NR ln Vf by Vi. But in case of the reversible process, this is for reversible process. Okay, reversible process, del S total is equal to 0. So that means we have different magnitude Okay, understand? So we have different value for del S total if the process is different. So it is not like that, that del S only for, system. The system del S is equal to 0. Sorry, not 0. It will be equal to NR ln Vf by Vi. We can use this formula for reversible and irreversible process to calculate the change of entropy for that system. But for the total entropy, it will not going to be, actually it will depends upon the process. Okay, but here this is not depends upon the process. We can use this one for reversible as well as irreversible process. Hope you understand this point. Okay, understand? But here again, here you see del S total is positive. Okay, that means what? Del S total for irreversible process is greater than 0, which we already know that for irreversible process the change of entropy is always greater than 0. It is already discussed in the second law of thermodynamics. Okay, understand? Always we know that the entropy is increasing for irreversible process. So this example also justify that concept. So now we're going to discuss about the second process, which is actually your phase transition. Phase transition. So phase transition is, I think you all know what is the phase transition actually. Phase transition is actually we have some idea. No, when we actually let us suppose we have some ice. Okay, so if we increase the temperature from 0 degree to 1 degree, then that ice will become water. So if we take that same water and you again apply some heat energy, okay, to increase the temperature up to 100 degree. Let's suppose we again add some extra heat to increase the temperature from 100 to 100.1 or 0.2, 100.1 or 100.2 or 101. Let's suppose then the water will become what? It will become gaseous system. That means vapor. Okay, so that at that that phase, that means one is solid phase, one is solid, another is liquid, another is gas. Okay, so there will be some interface now. That means the phase will going to one phase will going to going to become other phase at some particular temperature. Okay, so in case of ice, let's suppose this is if it is water. If in case of water, suppose water, okay, in solid state ice, so 0 degree, it is 100 degrees Celsius. Okay, so at that temperature actually that ice will become liquid and that liquid will become gas at 100 degrees Celsius, or you can say 373 Kelvin or 273 Kelvin. Okay, and actually this temperature, okay, this temperature, that means the phase change temperature, is known as transition temperature actually. Okay, and this is represented by TRS. Okay, capital T TRS, and this represent the transition temperature actually at which the two phases are at equilibrium at 1 atmospheric pressure. This is important. Okay, so this is actually transition temperature okay, at which the two phases are at equilibrium at 1 atmospheric pressure. Okay, so this is actually transition temperature, and actually this process, this phase transition process from this phase to this phase or liquid phase to gas phase, this process are actually at this position, actually that equilibrium position. Okay, this is actually what? Reversible process, and this is at equilibrium position. Actually this is actually reversible process. Why reversible? Because the two phases in that system are at equilibrium. Understand? So this is actually reversible process. This process is reversible, this process is also reversible process. Clear? So now coming to our main point, which is we have to calculate what we want. Actually our aim is to calculate the entropy change for this one, no? But here we actually term this one as del TRS, capital S. which actually represent the change of entropy for the phase transition process. Okay, so we have this Q. Q is equal to actually del H. Okay, so why del H? Because you see this process occur at constant pressure, because this phase transitions occur at under the 1 atmospheric pressure and normal laboratory condition, because in the earth in our earth surface, it is always the pressure is constant, which is 1 atmosphere. Okay, so actually we know that QP, that means the constant pressure, is equal to always change of enthalpy, and QV, that means the change of, that means the heat, which is we apply the heat now. Sometimes we introduce some heat to the system, and that heat is actually nothing but your del U. Okay, so if it is the constant volume, then it is del U. That means the change of internal energy is actually the heat applied to that system at constant volume, or the change of enthalpy is actually the heat applied to that system at constant pressure. So here, because this processes occur at constant pressure, so we can write Q is equal to del H. Okay, so what we can write here, you see this process, actually from here we can write del transition capital S is equal to Q transition capital T. Okay, understand? So here in place of this Q, that means the heat for this transition heat, actually Q transition means transition heat. Okay, transition is, we can write here enthalpy change, that means transition state, that means the enthalpy change for that transition, that phase transition, which is represented by del TRS capital H. Okay, divided by T, that means the temperature at which it will going to change their phases. That means here, if you consider the H, then it will be 273 Kelvin. Okay, for temperature. So the thing is that we have the relation now. That means we have the relation for, by using which we can calculate the change of entropy for the phase transitions. Okay, it may be this one or it may be this one. If we consider for ice, then we have to put here what, 273 degrees Celsius from ice to water. Okay, so if you consider from water to vapor, then we have to put here what, 373 Kelvin. Understand? So now the question is that again, so what about this process? Okay, if let's suppose the del SH is greater than 0, that means del transition. So I am forget this. You have to write this TRS. Okay, del TRSH. So if the transition enthalpy change is equal to greater than 0, that means what? That means if it is endothermic process, then what will be happen? Or if it is del TRS is equal to H less than 0, then what will going to happen? So actually, first let's suppose this one. So if this del transition H is equal to 0, that means the enthalpy of change of enthalpy for the transition process is less than 0, then the change of entropy is also less than 0, because we have to put this one, then it will be 0. So actually this indicate what? This actually, that means what? The entropy of this change of entropy for this transition process is decreasing. Okay, that means it will become less than 0. So this decrease of entropy is actually consistent with localization of the matter. What is the meaning of it? That means it will going to localize the matter. Okay, so that means the randomness will going to decrease. That's why the entropy will going to decrease. And energy, that means the energy is also going to localize. Okay, energy and matter will going to localize. That means the entropy will going to decrease. That accompanies the formation of the solid. That means formation of the solid from the liquid, or formation of the liquid from the gas. Understand? And in this case, for this one is what? This one is if the enthalpy change is less than 0, and this is actually exothermic process. Exothermic process. What is the meaning of exothermic process? Exothermic process is what? That means the heat will going to heat actually lost by that system. If the heat is lost by the system, that the temperature of the system will going to decrease. Understand? The same thing. So this is exothermic. And if the endothermic process, then this process is actually endothermic process. Okay, endothermic process. That means we have to apply some introduce some heat to the system from the outside, that means surrounding. That's why the heat of that system is going to increase. Actually, what is this? This is actually heat. You see, this is the heat at constant pressure. So the heat of the system will increase when we apply some external heat. So this is endothermic. So if the process is endothermic, that means we add some external heat, then it will add some at that transition enthalpy at that temperature, at that fixed temperature. Okay, it may be this one, or this one. Okay, the solid will going to become liquid, or the liquid will going to become gas. Understand? For that, so that means this process, and this process is actually endothermic process for solid to liquid and liquid to gas, and for the gas to liquid or liquid to gas phase transition, the process is actually exothermic process. So now the table actually 3.2, it actually exhibits some entropy of vaporization of several liquids at their boiling points. Okay, an interesting point is that a wide range of liquid exhibits same value of del vaporization S. That means the entropy of vaporization, change of entropy of vaporization, which is actually almost 85 joule per Kelvin per mole. And this experimental observation is known as Rodon's rules. Okay. So in this class we discussed about the the calculation of or how to calculate the change of entropy for the the expansion of ideal gas, actually expansion of isothermal expansion of ideal gases. Okay, and also for the phase transition. Okay, so the next class we will going to discuss about the heating and the measurement of entropy for heating. Okay.